Okay, so we're looking at these questions really quick. So the first one, we're saying which of the following describes a difference in the behavior of an electrically conducting sphere and that of an insulating sphere. So if we look at these just kind of going through process of elimination, a conducting sphere can be charged by friction, but an insulating sphere cannot. Well, we know that that's not true. We know that an insulating sphere can be charged by friction. That's what happens whenever we have a balloon. We'll say, hey, we have like this fur, we have this object, and it's got these electrons, so they're just kind of chilling on there. But we say, oh, this balloon or whatever, this insulating sphere has a larger electron affinity, so when we rub it on there, the electrons will stick to this insulating surface and stay where they were, but we know that an insulating sphere can be charged by friction. An uncharged object can be charged by touching it to a charged conducting sphere, but not by touching it to a charged insulating sphere. So with this one, we can charge objects by touching them to an insulating sphere. Yeah, we can touch it and say, hey, this is a conductor, and have these electrons kind of jump to it. So this one's not true. We can charge with a insulating sphere. When a conducting sphere is brought near a positively charged object, some of the sphere's electrons will move closer to that object. No polarization occurs in the atoms of an insulating sphere. So that's not true. We can polarize an insulating sphere, it's just not as intense. So this right here is an example of a conductor. The electrons, they're free to move. If we have a positive object here, they're free to move, and they can kind of create this polarization where you have this negative side and this positive side, and it's kind of a strong polarization. With an insulating sphere, we can still get a polarized object. It's just much more weakly polarized. If we bring a positive thing here, these electrons, we said, they can kind of shift around in their little compartments. So they won't be able to fully move, but we will still be able to get a side that's weakly negatively charged and then weakly positively charged, because these electrons, even though they're tied to their proton and they can't really freely move, they can still shift around. These electrons are still on the outside, they're still in these kind of like orbitals, so they can still shift, but they can't fully move. But they still are polarized, it's just weakly polarized. Then this last one, excess charge placed on a conducting sphere becomes distributed over the entire surface of the sphere. We know that's true. They want to distribute themselves so they have this maximum distance. Excess charge placed on an insulating sphere will remain where it is placed. Yeah, we know that that's true. An insulator, it'll just kind of stay, and it'll be kind of bound to these protons where we put them. With this next one, two charged objects are held a distance d apart. Their mutual gravitational force is equal to their mutual electrostatic force. Which of the following must be true of the charges and masses of the object if charge is expressed in coulombs and mass is expressed in kilograms? So our standard units. Here we say, okay, well, the gravitational force is equal to the electric force. These r squared are going to be the same thing. So we can say it's g m1 m2 has to equal k q1 q2. And we know from our units or our equation sheet that g is very, very small. G is 6.67 times 10 to the negative 11th, and k is 9 times 10 to the 9th, so a very large number. So k is very large, g is very small, but these two things equal each other. So that means that m1, m2 has to be large, and q1, q2 has to be small, so that we can have this balancing out and that these two sides can indeed equal each other. So this is going to have to be this one, the magnitude of the product of the charges must be much less than the magnitude of the product of the masses. Alright, for this one, two electrically neutral conducting rods are near a negatively charged sphere as shown in the figure below. Rod 1 is touched to rod 2 for several seconds, and then the rods are separated. The rods are then both removed from the vicinity of the charged sphere. Which of the following best describes the resulting net charge on each rod? So these rods are conductors. When we bring them next to each other, they kind of become one object, and the electrons are going to be repelled from this negative sphere, and they're going to go as far away as they can. So a lot of our electrons are going to go to this second rod. They're going to be able to move here because we have this solid conductor essentially. So they'll be able to just move over there, and we'll get a lot of negatives in rod 2. When we separate them, and we're keeping them still over here, we'll keep that separation where we have a positive rod 1 and a negative rod 2. So that separation will still hold. So rod 1 is positive, rod 2 is negative. When a negatively charged object is brought near but does not touch a neutral object, which of the following best represents the interaction? So with this one we're saying, okay, we have this neutral object, or we have kind of this nice little neutral, yeah, everything's neutral. we bring a negatively charged object near it, and well, the electrons in this neutral sphere are not going to like that one bit. They're not going to like this negative sphere. So they're going to say, hey, we don't like that. And they're going to run to the other side of the sphere. They can do that because it's a conductor. They can move wherever they want, which leaves a positive side on our originally neutral sphere. This positive side will attract the negatives over here, and we will have this attraction because the positive side and the negative side are going to attract each other. So whenever we bring a conducting object or a charged object next to a conducting neutral object, we will get an attraction because we have this little bit of polarization. And the last one is kind of like question 2. We're saying, hey, the force, we want to figure out the ratio of the gravitational force and the electric force when we move them away from each other. What we can set up here is our equation for Fg and Fe. We got Gm1 m2 over r squared, kq1 over, or q2 over r squared. The r squared are going to cancel. That distance is going to be the same exact thing. So we end up with Gm1 m2 over kq1 over times q2. And what we know is that these are not distance dependent. M is not distance dependent, or q is not distance dependent. So even if we move them, the mass stays the same and q stays the same because those are inherent to our objects.